So here we are, we're in lesson 1.9. We're formalizing our discussion about scientific notation. And the first example is this one right here where we say Luisa is researching the approximate distance between the Earth and the Sun. Her father told her the distance is 9.26 times 10 to the 7th. In an astronomy book, she found this diagram that shows the Sun and the Earth being 92,960,000 miles. And the question is, which of these numbers is the correct estimate or the correct measurement of the distance? And as it turns out, this situation is a little bit more complicated because the distance between the Earth and the Sun does change somewhat during the course of the full orbit of a year, but this is the figure that's accepted as a normal number to use as a standard. Anyway, it's really easy to figure out what's going on here. If we use scientific notation, this is the number that was given by her dad, which is written as a number that is one digit to the left of the decimal times the power of 10. Whereas this number, if I actually do that multiplication, I multiply 9.26 times 10 to the 7th, that's going to move the decimal 7 spots to the right, because each power of 10 creates a number that's 10 times bigger. 10 times bigger means one more place value has been added. So let's try one here. It says the height of Angel Falls, the tallest waterfall in the world, is 3,212 feet. How do you write this number in scientific notation? Now, here I'd like to pause and say that we really typically, the purpose of scientific notation, the reason that we like it, is it makes it easier to write really large numbers. This is not a super large number, and what we're going to end up with here isn't going to look any less complicated than this. So bear in mind that the most practical use of it is when the numbers are very, very large. In this case, not so big. But in any case, I know I've got to get this to the form of some number that basically is non-zero but less than 10. It's got to be at least a single digit times a power of 10. So to get the decimal to where it needs to be, I basically have to move the decimal to right between the 3 and the 2. So in this case, 3.212 times. Now, what's the power of 10? Well, I moved the decimal 3 times, so that becomes the power of 10 that we'll use. So our final answer here, 3.212 times 10 to the third. In this slide, now we're talking about using scientific notation for really, really small numbers. It's exactly the same process, except that the decimal is actually going to be moving to the left, which means the exponent is going to be negative. Because remember, negative exponents mean a reciprocal. That means the number is in the denominator of a fraction. So our numbers that we're working with are all numbers that are not only less than 1, but a lot less than 1. So this number right here, over here on the blood cell, is expressed as 0.0000703 meters. That's very, very small. So what we want to do is shown right here. Basically, the decimal is here, and it needs to be to one spot to the right of the first non-zero digit. So find the first number that's not a 0, plop the decimal down just to the right of that, and then we count. Well, you saw we moved it 6 times, so our exponent is -6. So again, this isn't as small of a number as in our other example, but it's pretty small. It's quite a bit less than 1. In fact, if I wrote this number right here as a fraction, let me make my pen a little bigger, I would write it as 5/1000ths. That's a pretty small amount. That's basically 0.5%. So to do standard notation, I start with the number I'm given, or scientific notation. This right here, sorry, this is standard notation. We're looking for scientific. So a number times a power of 10. So what I'm going to have to do is I'm going to have to convert this into a number that's got at least 1 digit. So I'm going to have to move the decimal from where it was here to where it is now. Right? 1, 2, 3 times I'm going to have to move it to put it there. And remember that I'm talking about a really small number, and so my exponent is going to be negative. So it's 5.0 times 10 to the negative third. Make that the same color. Now this process using a calculator is really easy. If you're being asked to take a number that's written in scientific and put it into standard, you could literally just type this in right here on your calculator. But what you'll find is you won't really need to do that once you get the hang of it. You'll just know that all I have to do is take this decimal place and shift it to the right 15 times, which is going to give me, I've got one digit to get past, and then after that, I've got all zeros. So I say, well, I'm going to move it 15 times. The first time we'll get it here, and then I'll have 14 more zeros on top of that. Same thing with a negative exponent. If I'm given this number, I could very easily just compute the value of this on the calculator, and the calculator will give you something that looks like this. It's just important that you understand when you see these numbers on the calculator, what they're telling you is that's the base and that's the exponent. Here, 8 is the base and negative 9 is the exponent. Because we basically, when we multiply by a power of 10, another way to think about this is like 8 over a million. So it's 8 millionths. Obviously, that's a really, really, really small number. So that's why we move it 9 times. So just to recap here, the key concept, when I'm converting numbers from standard to scientific that are very large, like this one, I basically count the number of digits it would take to get the decimal just in between those first 2 digits. So I've got a 1-digit number, and then I count those. That becomes my exponent. And when it's a really small number, I'm going to move the decimal to the right, and however many times I move it to the right to create a single-digit number becomes an exponent that is negative. Okay, last slide here. Let's just try 2 quick examples. To write this first number in standard form, what I'm going to do is I'm going to multiply this times this. Now, if I look carefully, I see that I'm going to be moving the decimal place 18 times. Now, if I look carefully, I also realize that the first 3 places are what I'm going to do just to get the decimal past those other digits. And then, so that means after the first 3, I've still got 15 exponents left, or 15 decimal places that I'm going to move. So I'm going to write the number 9225. And again, remember, 1, 2, 3 is the first 3, and then there are 15 more. I'm going to think of that as 5 groups of 3. 2, 3 groups of 3, 4 groups of 3, and 5 groups of 3. And you can see from this example, this is the power and the advantage of scientific notation. That number is really large number, and it's a pain, literally and space-wise, to write that. So scientific notation, though it looks complicated, was developed as a way to make things easier. It takes up less space. So let's look at example B. Now I've got a negative exponent. So I'm going to move, I know I'm moving my decimal 8 times to the left, and I also know that the first move I make is just going to get me past the 6. So that means there are going to be 7 zeros to the left of that. And then, between the 6 and the decimal point, there are going to be 7 more zeros. So let's go. Here's the 0 that just holds the place for us, and then there's the decimal. 1, 2, 3, 4, 5, 6, 7, 6, 3. Right? 7 zeros plus that extra space I had to move it to get it past the 6.